And if you do have any questions, go ahead and put them in the chat and we'll go over them at the end. I am going to be using you guys as the guinea pigs. I want to try some poll questions this presentation. So play along, tell me if you hate them, but I just want to test them out. So we'll be doing those throughout the presentation. And if you do need a PDH credit, make sure that your display name is something that I can match you up with on how you registered. And with that, Dan, I will hand it over to you.
Kelly, thank you very much. And thank all of you for joining us today for another session of Webinar Wednesday, Psychrometrics Deconstructed Part 2. We're going to take up where we left off in the previous session. First of all, with a review of all the terms we covered, or the psychrometric terms we covered in the August session. Then we're going to look at the psychrometric processes for various MEP or mechanical systems. We're going to look at medium pressure variable air volume systems and the psychrometric process across a cooling coil. Then we're going to look at whether or not supplying 55 degree, 54 degree air off a cooling coil is adequate to control building humidity as our buildings become more efficient and less airflow is required to meet peak sensible design requirements. We're going to look at controlling our sensible and enthalpy heat recovery solutions and the psychrometric process involved with that approach for reducing building energy requirements. Then we're going to look at some high performance air handling solutions for high performance HVAC systems. We're going to look at air handlers for displacement ventilation systems and how they work psychrometrically and what we should be aware of when we do so. And then we're going to look at the psychrometric process for DX DOAS units. So let's begin. There we go. Sorry about that. Okay. Psychrometrics terminology, a quick review. In Psychrometrics Part 1, we argued that the fundamental purpose of an HVAC system is to simply move energy. We need to move energy in order to maintain building set point conditions for temperature and also humidity levels in the space. So in order to provide cooling in a building, we need to move as much sensible heat energy from the building as possible as the building gains throughout the day and deposit that energy outdoors, as well as any humidity buildup during the day that needs to be deposited out of the building in order to maintain relative humidity conditions during our wet times of the year. So in order to do that, we need to calculate the amount of total load, which is defined as the sensible energy plus the latent energy in the building. Well, how do we do that? How do we calculate that? We apply the psychrometric chart. To remind you, the psychrometric chart is simply a reference chart. If we know a state point on the chart defined by two air properties of air, such as dry bulb temperature and wet bulb temperature, or dry bulb temperature and relative humidity, we can determine any other air property of that air state at any given condition. So this is very important because it gives us an opportunity to understand absolutely what forms of energy exist within a sample of air and how we need to, and how much energy needs to be moved in order to maintain our building at its set point conditions. So psychrometrically, there are several different processes. We have sensible heating, where we actually add heat or thermal energy to a sample of air, driving the state point to the right from a given state point when we heat air. We have sensible cooling. We have humidification, where we add water or moisture to a sample of air without increasing the dry bulb temperature. We have dehumidification, where we remove humidity from a sample of air without removing temperature. There's the process of evaporation. There's the process of chemical dehumidification. where we apply desiccant forms of dehumidification. We have heating humidification, and then we have cooling dehumidification, the process that we see across cooling coils and air handlers. The previous session, we also discussed the topography of the psychrometric chart and where to find the dry bulb temperature, dew points, humidity ratios, etc. on the psychrometric chart. And we defined dry bulb temperature. To apply the psychrometric chart, you need to make sure you understand the fundamental terms of the state points that are illustrated on the chart. So there's dry bulb temperature, which is the value, measures the value of energy present in a sample of air at a dry thermometer. It is otherwise known as sensible heat energy. And once we know the temperature, we find the dry bulb temperature that is illustrated on the x-axis of the chart, and a line is drawn through that temperature value parallel to the dry bulb temperature lines, which are left-leaning vertical off of the x-axis. There is relative humidity on the psychrometric chart. Relative humidity is defined as the moisture content in a sample of air as a percent of the total amount of moisture air can hold when fully saturated. So what is relative humidity relative to? Temperature, because the temperature or thermal energy in a sample of air determines how much moisture an air sample can hold at that temperature. So the relative humidity lines on the psychrometric chart span from lower left in semi-parabolic curves up to the upper right of the chart. So where you have a sample of air that measures at a condition of 72 degrees dry bulb and 40% relative humidity, you can find a state point on the chart, and by drawing a line from the dry bulb temperature up through the chart, and where that line intersects with the condition of relative humidity, a state point is achieved, and that's your starting point. Then from the chart, we can actually show what the wet bulb temperature is. Most air handler schedules, or all air handler schedules that I've seen, represent the total load in dry bulb and wet bulb temperature. So where does the wet bulb temperature, what is the definition of the wet bulb temperature? It is the lowest temperature air is cooled to by water evaporating into a vapor on a sling psychrometer. And we illustrated what that psychrometer looks like and defined it in the previous session. So the rate of evaporation of a moistened wick on the psychrometer impacts the temperature reduction on the wet bulb thermometer. The drier the environment, the greater the evaporation, the higher the reduction of temperature. The more humidity present in a sample of air, the less evaporation, and the higher the wet bulb temperature. So wet bulb is a very good metrics for determining how much moisture is present in a sample of air. So to find the wet bulb temperature on the psychrometric chart, if you understand a state point at 72 degrees dry bulb, 40% RH, you look for the wet bulb lines along the 100% saturation curve in the uppermost border of the semi-parabolic relative humidity lines, and where that line intersects, through the saturation curve, you will have a temperature value known as the wet bulb temperature value. The psychrometric chart also has dew point, which is the temperature at which there is not enough energy present in a sample of air to keep water in a vapor state and it condenses to a liquid, a temperature that's necessary to control building humidity. So the good thing about dew point, unlike relative humidity, is the fact that dew point is an absolute measurement of the water content in a sample of air. So as temperature changes, dew point still remains the same, providing you maintain the same amount of water in that sample of air regardless of temperature. So the dew point lines we find on a chart can be illustrated in this way. Once the state point is determined, and we draw the line from the dry bulb line through the state point, we actually look for the dew point line, which is parallel to the x-axis. So a straight line parallel to the x-axis is drawn through the state point, and we can calculate the dew point temperature either with a dew point reference line to the right that is parallel to the y-axis, or in this rather in a different way as well, through the wet bulb temperature, where the wet bulb and dry bulb equal each other. If the wet bulb and dry bulb temperature equal each other, that is the dew point. In this condition at 72-40% RH, 46.4 degrees. There is specific humidity, which measures the mass of water in a sample of air, referring to grains per pound of water. There are 7,000 grains per pound of water. Specific humidity is also an absolute reference to water content in a sample of air, regardless of temperatures. The specific humidity lines are parallel to the x-axis and the dew point lines. So to determine how many grains of moisture in a sample of air, you define the state point in this condition of 72 degrees, 40% RH. You draw a horizontal line through the state point on a different line reference parallel to the y-axis to the right of the chart. You will find the specific humidity reference line, and it'll illustrate that at that condition or that state point, there are 48.7 grains of moisture per pound of air. There is also absolute humidity, which measures the amount of grams of water in cubic meters of air. So that is a different absolute reference, but using the weight of water as opposed to grains in a sample of air. And then with all of these points, we can calculate how much energy is in the sample of air, and that is the goal of the whole psychrometric process, is to understand how much energy the mechanical system needs to move to maintain buildings in stable set point conditions. So enthalpy is defined as the total energy in a sample of air, and it is comprised of the total sensible BTUs in a sample of air, as well as the latent BTUs that keep water in a vapor state. So the enthalpy line on the psychrometric chart is that diagonal right leaning line from the lower left to the upper right, and it gives BTU values along that line. So to calculate how much energy is present in a sample of air at 72 degrees and 40% RH, again, we do the same process that we did with the other processes. We determine the dry bulb temperature, draw it through the state point, and then draw a diagonal parallel to the wet bulb lines. And where that line intersects the enthalpy line, a BTU value is given. In this sample of air, we notice that there are 24.9 BTUs within 1 pound of air at 72 degrees and 40% RH. So this is how you can determine how much energy is present in a sample of air and how much energy needs to be moved if you want to go from one state point of air to another state point of air to maintain building set point conditions. So let's look at the psychrometric process for medium pressure VAV systems, or the common psychrometric process across a cooling coil. We're going to use a 20,000 CFM air handler as an example that is actually bringing in 20% outside air and 80% return air at the conditions illustrated. We're using Phoenix, Arizona's peak summer design condition in monsoon, which is not necessarily 115 and 120 degrees. Our peak summer design condition is usually monsoon, and many engineers use an outside air condition of 97 degrees dry bulb, 76 degrees wet bulb, or 70 degrees dew point. We use a winter condition of approximately 32 degrees, though it can get colder sometimes for 1 or 2 nights a year in our midwinter months. We're going to look at a return air condition of 77 degrees because there's usually some thermal gain above the room or a room set point condition the return air is drawn from. So we're going to add 2 degrees of dry bulb temperature to that sample of air. And then we're going to mix these 2 volumes of air together. And when we do that, we have to calculate for the cooling coil the new state point for the mixed air condition. In this case, at these percentages of outside air to return air ratios, a mixed air condition of 81 degrees dry bulb, 66 degree wet bulb is achieved. And we're going to try to condition that air by providing 44 degree chill water through that cooling coil in order for that air sample to achieve saturation on the psychrometric chart, otherwise represented at 100% RH. So there's insufficient energy in a sample of air to keep water vapor in a gaseous state, and it condenses to a liquid and filling cooling coil draining pan. So that is what needs to be determined first of all before we look at the psychrometric process across the coil is what is the entering air condition. So we've determined that we're going to provide 55, 54 degree airs to provide a dehumidification application to the cooling coil. We're actually cooling the air from the mixed air condition, and we are going to approach the saturation curve on the psychrometric chart to provide the proper dehumidification that we hope to achieve. So condensation begins to occur on the chart, as can be seen, as that line begins to approach the leaving air condition. Now you'll notice that that is not a straight line to the saturation curve when there's dehumidification. You have sensible dry bulb cooling at first before you start seeing some dehumidification, and that's due to the residence time of the sample of air in the cooling coil. It takes a while for that air as it passes through the coil, though it happens actually very rapidly. And that resident time brings about a gradual reduction of the mixed air temperature to the 55 degrees necessary for condensation to occur. So if we look at the process, let's look at the cooling coil hitting 55 degrees. And when we look at the psychrometric chart, we notice that there's a 26 degree dry bulb temperature reduction to take mixed air at 81 degrees down to 55 degrees. And you can calculate the amount of sensible energy or thermal energy necessary to bring about that reduction of heat. And that's by applying the equation of total sensible heat load of 1.8, which is a constant, times the airflow, times the temperature differential from the mixed air condition to the leaving air condition. That equation results in a total of 561,600 BTUs of energy that needs to be removed in order to cool and dehumidify a sample of air Sorry, it's, there we go. Okay, so that being said, what about latent heat removal, or what about dehumidification of the air and the removal of the latent heat? How much latent energy needs to be removed to go from 81 degrees to 55 degrees? Well, if you look at the dew point of the mixed air condition at 58.3 and you look at the dew point of the leaving air condition, that's a 5 degree dew point depression. Or if you look at the specific humidity, that is a depression of 12.7 grades of moisture per pound of air. So moisture removed is approximately 150 pounds per hour. There's an equation to calculate latent energy, and that is 0.68 constant times the airflow times the differential in the grains of moisture that are to be removed. In this case, the calculation results in a value of 172,720 BTUs of latent energy that needs to be removed. So if we look at the overall process with regard to total energy, utilizing our enthalpy line, we will see that a total amount of 734,320 BTUs of energy need to be moved from a sample of air to bring air to the leaving air condition necessary to maintain our building conditions as a constant. So that demonstrates psychrometrically what happens to air through a cooling coil when it's properly designed to maintain space set point and humidity levels. And then we examined in the last session the penalties of reheating air once we've had to bring it to dew point, and we see reheat used regularly in offices and especially in healthcare facilities where we need to maintain humidity levels at between 30 to 60% in order to maintain healthy environments. So if we look at the psychrometric process of cooling the air and then having to reheat the air back up to 85 degrees to heat in perhaps perimeter zones during the winter conditions, we are doubling the energy usage to meet that at a VAV box. In fact, we have to add 25,900 BTUs at an 800 CFM VAV box in order to reheat the air to maintain the heating demand in a space that has to be maintained at stable temperature and humidity levels throughout the year, such as a hospital. So with that being said, Kelly?
So our results are interesting. On the poll question was, do you have humidity issues on any of your projects? Split right down the middle, 50-50.
Interesting.
Yes and no. Yep.
Okay, all right. Well, let's examine perhaps one reason why, and we're going to examine it applying the psychrometric chart. Let's look at a space condition designed to 75 degrees, 50% RH. And I use healthcare frequently because healthcare environments have to be maintained 365 days out of the year at their design conditions for not only temperature, but also relative humidity. So humidity and latent energy present in a hospital space is significant. So we're going to look at 75 degrees, 50% RH. Sorry, I don't know what. I don't know what's causing this.
It's every time I launch a poll. Sorry, Dan. I think you just have to click back on your slide.
Oh, okay.
Yep, sorry about that.
No, that's all right. As long as, okay.
Took me a minute
First
to
time
notice
we've
the
done
pattern.
this.
Yep.
You got it. Okay. And then I made the disastrous mistake, and I know better, and I have no good apologies. I tried to adjust my display settings on 3 screens prior to the presentation. It didn't work out, and I'm living with the results, so excuse me for that. But anyway, so let's look at the actual zone dew point at 75 degrees, 50% relative humidity. It's 55.13 degrees, the space condition, and that is the dew point. So the humidity challenge is a dew point temperature in the space of 55.13 degrees. Please remember and keep in mind, to control humidity in a building or in a zone is to control dew point, not relative humidity, because relative humidity is temperature dependent. It's relative to temperature. Dew point is absolute. So that is one of the reasons why ASHRAE 62.1 2019 moved from relative humidity to dew point. So let's examine this a little more closely. If we look at our process and we look at our space condition and the air handler providing 55, 54 degree air off the coil, look at the dew point of the supply air condition. It's 53.35. And we can illustrate that very clearly on the psychrometric chart. Well, the coil leaving air temperature is 55 degrees at 53.35 degrees dew point. Well, that's a 1.8 degree dew point depression. And that used to work fine in Phoenix, Arizona 20 and 30 years ago because we had to use a lot of air to hit our 115 degree design condition, and energy was cheap. We just pushed a lot of air through the building to do that, which at a 1.8 degree dew point depression, you can get under the limbo bar of tolerance. But as buildings are becoming more and more energy efficient, our peak sensible design days, our airflow requirements to meet our peak sensible design days are going down. Our airflow rates are going down, but humidity is not going down. And I really have to thank this education and awareness due to Munters that has some great information on dew point control. So anyway, that is the growing challenge. As Standard 90.1 advances and develops, building sensible loads are going down, airflow rates to meet the sensible peak load is going down, but humidity has not gone down. So it begs us to ask the question whether or not a 1.8 degree dew point depression is sufficient to control building humidity, especially if you live in the south central United States or southeastern coastline or whatever. So just one way to look at space humidity control a little more effectively, and it was due to the advice of Jay Eldridge of Daikin that gave me a target to examine when I wrote the Engineered Systems magazine article on 100% outside air variable refrigerant systems with decoupled outside air. He said, Dan, try 50 degrees off the coil. Well, that calculates out to 48.44 degrees dew point. We can easily find that condition at 53.13 on the psychrometric chart. We draw now the dew point line through the leaving air condition on the chart, and we notice that now the building humidity can be controlled at 6.7 degrees dew point depression. So that offers you a better solution. Now that begs another question. If it's a chill water system, does that mean chill water temperatures need to be lowered from 44 to 42? The answer is very possibly. That is one way to do that. But what happens to your chiller plant efficiency in doing that? Well, it becomes less efficient, it becomes more inefficient, I should say. So anyway, that is one way to provide proper humidity control in a building during our peak humidity design days, and something to keep in mind for future to avoid the challenges that humidity can often bring to a building. So let's look at another process psychrometrically. Let's look at sensible and enthalpy heat recovery and compare how they look on the psychrometric chart with regard to energy. So what is the purpose of energy recovery? Energy recovery is used to precondition outside air to reduce the outside air temperature or to increase the outside air temperature depending on whether in cooling or heating mode by exchanging energy from the exhaust air stream of a building into the supply air stream of a building. So there are two methods for doing that. There is a method of enthalpy whereby a heat exchanger, in this case shown as an enthalpy wheel, actually transfers both sensible and thermal energy and latent energy from the exhaust airstream to the supply airstream. And then there is sensible only heat recovery where only thermal energy is transferred. So we're going to examine both of them and how those processes look on the psychrometric chart. Let's look at the 20,000 CFM air handler that had an outside air requirement of 4,000 CFM, and that's what we're going to look at our airflow requirement. And then to determine how much exhaust air, we have to make sure that the exhaust air is less than the outside air to maintain your building positive pressure, which is usually at about 0.01 inches of static. So exhaust air is often less than the outside air to the space. Well, if we look at this process and we look at a sensible heat exchanger process, we have a sensible thermal energy transfer effectiveness of approximately 88% or 89% with this process, depending on summer or winter conditions. So let's look at it psychrometrically, and let's look specifically at the cooling process. If you use a plate and frame sensible heat exchanger, you'll notice that there's a decrease in the outside air, transferring energy from the outside air to the exhaust air stream because of the thermal imbalance of energy. And as we discussed in previous sessions, that wherever there's an imbalance of energy, a high energy state always moves to a low energy state. So if we look at using a plate and frame heat recovery unit, we can actually get a reduction in the outside air of roughly 15 degrees, which looks at a sensible heat depression of 15.1 degrees. That calculates in an energy savings to the building of 65,232 BTUs. So that's substantial during the peak summer design condition. However, if you look at the latent energy depression, there is zero in a sensible heat recovery solution, which may make sense if you live in a very dry climate. Could make all the sense in the world, and there are various other considerations as well. But again, you can see psychrometrically that the latent component is unchanged during sensible heat transfer. Let's look at energy recovery for an enthalpy wheel, or even an enthalpy box that is currently available by some of the manufacturers that we represent. We're going to look at the same conditions, the same volume of outside air, 4,000 CFM. Look at the total effectiveness as opposed to just the sensible heat transfer effectiveness of the sensible heat recovery solution. Total effectiveness can range anywhere between 70 to 80% by using an enthalpy solution for heat recovery. And let's examine why on the psychrometric chart. First of all, you have your outside air condition and entering the box or the energy recovery device. Then you look at the leaving air condition. Here, the sensible depression is 13.9 degrees, or approximately 58,000 BTUs. But look at the latent energy depression. It is substantial. That's the amount of energy necessary to keep water in a vapor state. And that can be easily seen and calculated on the psychrometric chart. So what does this mean with regard to total energy savings to a building? Using an enthalpy wheel in a building that is actually preconditioning 4,000 CFM will result in 182,000 BTUs of energy savings on that project. So it is a very good solution for reducing the amount of building load, I'm sorry, not building load, but outside air load on your system that can often result in a lot of energy savings. In this example, up to 15.23 tons.
So the results for our last poll: are you being challenged in your designs with the new standard 90.1 requirements? We had 56% say no and 44% say yes.
Interesting. All right. Well, let's look at some of the solutions that are going to help with the challenges that standard 90.1 provide us. I have a presentation, now in fact I gave it I think in July, on 90.1 2022. The Department of Energy has issued the determination that 90.1 2022 will be the energy benchmark for buildings, for all future buildings and any building remodels, etc., because it adds another 9.8% efficiency above and beyond the 2019 edition of the standard, which offered only 4.7% more efficiency to the 2016 standard. So ASHRAE is being very aggressive, and the industry is being very aggressive to make our buildings more efficient in order to meet our decarbonization initiatives in the future. Well, one of the solutions that I think makes very good sense, especially in our dry southwestern climate, is displacement ventilation. Okay, here we go, Kelly, our challenge again.
I did just launch a poll.
Did you?
Yep. Would you like to know the results of these ones? They're still, the answers are still coming in. But the question was, are you using any MEP design strategies other than medium pressure VAVs to meet the new building standards? So as you begin to talk about other solutions, we've had 33 people respond so far, and more are coming in, but we're sitting at 58% that say yes, they do use other solutions.
Interesting. Well, let's examine what that means psychrometrically for one solution, which I think is a solution that will be given more and more consideration, and that's displacement ventilation. And I say that for a number of reasons, but let's stay focused, which could sometimes be a challenge for me, on the psychrometric process of displacement ventilation. What is the goal of displacement ventilation? It is to create a thermally stratified space environment. Unlike a conventional MEP system that is an all-air system that seeks to achieve a thoroughly mixed environment within the space, displacement ventilation wants to maintain a thermally stratified environment. By doing that, it provides 62 to 68 degree supply air at low velocity off of displacement diffusers or through the floor and underfloor air systems, and allowing the air to stratify throughout. So if you provide 62 degree airs, your floor will be at a temperature of about 70 degrees, the thermostat 75 degrees or whatever set point is assigned. And then as heat energy builds up in the space, that warmer energy convectively flows to the upper level of the room where your exhaust and return air grills are located to eliminate that energy from the space. So what moves air in a thermally stratified environment? Heat. Thermal energy is the mover of air through convective plumes. So it's a rather elegant solution, and I've used it a number of times and have a couple of firsts in actually using it in patient rooms at the Banner Boswell complex. It worked very well. Well, the reason why you might want to look for this solution is, for one thing, they're low static pressure systems. Second thing is you can reduce your fan energy. And thirdly, you can, in Phoenix, Arizona, double your economizer hours by providing 65 degree air versus 55 degree air. So some of the motives for it. Well, how do you condition the air to arrive at 62, 65 degrees and yet maintain a dew point on that supply air adequate to maintain humidity levels? Well, one of the solutions I've used in the past is side stream bypass. You have an air handler with a plenum section attached that spans from the inlet to the outlet of the cooling coil with a modulating damper at the inlet that is connected to a discharge temperature sensor at the air handler that modulates the unconditioned mixed air, open and closed, to put it into the supply air stream post coil to provide free reheat of the air. So let's look at that psychrometrically. Well, first of all, we need to look at the mixed air condition that we illustrated earlier for the VAV systems, for the VAV medium pressure air handlers. And we've got a mixed air condition here of 83 and 66, 67 degrees. We're going to provide 44 degree chill water to a chill water coil to allow the supply air to achieve 55 degrees for dehumidification. You have to dehumidify, but this is the secret if you use side stream bypass for an air handler, for a displacement ventilation air handler. You have to make sure you have sufficient dew point depression across the coil whenever a mixed air is being dumped into the supply air stream downstream of that coil in order to effectively control humidity. So let's demonstrate that psychrometrically. First of all, you have to bring the air in a displacement ventilation air handler to saturation off the cooling coil, which suggests in this particular example 28 degrees. And if you calculate the actual energy involved in that, that is a total sensible heat calculation of 4,800 BTU. So we've got to bring the air to saturation. So let's look at that psychrometrically. that is bringing the, you have a room that's at 55.13 degree dew point. We now bring the air to saturation at 55.54. Well, that's 53 degree dew point, as we already mentioned, and we've already raised the argument, is a 1.8 degree dew point depression adequate for displacement ventilation air handler across the cooling coil? Well, probably not, especially if you looked at when you opened up the mixed air bypass section in order to raise the supply air temperature from 55 off the coil to 65. In this example, we're going to bleed 7,250 CFM of mixed air at the mixed air condition into the supply air stream. We look at the psychrometric chart, draw our dew point lines through the space condition, and then we draw our dew point line through the supply air condition at 65 degrees, 58 degree wet bulb, or 59 degree wet bulb. That's a dew point of 55.03. So you can see that leaves you with approximately a 0.1 dew point depression if you try to hit 55 off of a coil. And using side stream bypass, you could run into humidity issues very quickly. So let's examine this more closely if we provide a lower leaving air condition off the same size cooling coil, and what challenges that might present for us. Well, you do get better dew point depression in doing that. It's going to be 1.3 degrees dew point depression by bringing your air to 5250 off the coil before bleeding in 8,500 CFM of mixed air to elevate that 52 degree air up to 65, which is going to have the moisture in that mixed air adding humidity back in. So it provides you a better cushion of a 1.83 or 1.3 degree dew point depression as opposed to 0.1. Anyway, that would be the solution to do it, is make sure that the cooling coil is properly sized for displacement ventilation to achieve the dew point necessary so that it can absorb the moisture content in the mixed air when it's applied post-cooling coil to bring 55 or 52 degree air to the leaving air condition, whatever it's designed to be, 62, 65. So anyway, something to keep in mind when using side stream bypass. A more controlled approach for displacement ventilation units is using perhaps a DX unit with hot gas reheat solution, or possibly using a dual wheel unit where you have a sensible heat exchanger downstream of the cooling coil that post-heats the supply air off the coil by the energy absorbed from the exhaust air stream in that design solution. Okay, another high-performance HVAC solution is the units used for 100% outside air systems, such as chill beams, passive radiant cooling and heating systems, and for variable refrigerant systems, which had demonstrated to provide a higher level of energy efficiency for variable refrigerant designs. So let's look at a DOAS unit and its design condition. We're going to actually use for chill beam systems a strategy with regard to the total load, and the total load will be decoupled into its latent and sensible components. DOAS units are designed optimally to provide only the outside air necessary to meet the ventilation loads within that building. Now in Phoenix, that can be a challenge. We may need to do some supplemental sensible cooling in our peak summer design day. But regardless, that's the goal of it, because you want to shift as much sensible load to a more dense heat transfer medium. In this case, it's water that's passed through chill beams or passive radiant cooling and heating devices in ceilings, or to refrigerant that we would see in variable refrigerant systems. So let's look at our building, sample building size of 20,000 square foot. And with 100% outside air systems, because so much building sensible load is driven to a more dense heat transfer medium, such as water, then we can significantly reduce the airside component. Because it requires, and you want to do that because it requires a lot more energy to provide fan energy in a mixed air system than it does energy required for pumps to move water, a more dense heat transfer medium, through a building. So let's look at a dough ash unit. One of the characteristics of this particular sample that we're going to look at is, again, a total of 7,000 CFM of airflow through the dough ash unit. We're going to provide a supply air condition of 50 degrees wet bulb in order to maintain adequate dew point to prevent humidity challenges in the space. And we're going to adjust the exhaust air side to 6,400 CFM at a 63 degree condition. If you have a hot gas reheat coil, you can provide easily a leaving air condition of 60 degrees, maybe even 65 degrees on a DX dough ash solution. So looking at the dough ash unit psychrometrically, you have your outside air condition and you have your room condition. And if you look at the energy recovery component of a dough ash unit, which is used because you are actually exhausting the amount of air that is supplied through the dough ash through a dual tunnel unit to allow for energy capture of the exhaust air to precondition outside air. So we see substantial savings in providing an enthalpy heat recovery solution in a dough ash unit. In this particular case, 105,000 BTUs of sensible heat recovery and 119,000 BTUs of outside air latent recovery. So once we use the energy recovery device in a 100% outside air unit to precondition the outside air, let's look at the coil conditions. Let's look at the entering coil condition of 83 degrees off of the heat recovery device, and then look at the leaving air condition off the coil. That shows a total sensible heat transfer or sensible heat load of 235,000 BTUs. So if we look at the latent component and we run the calculations from an enthalpy wheel, we can actually save 142,000 BTUs by drying out the outside air before it even hits the cooling coil. And that means that a total dough ash unit load is now 377,000 BTUs versus 724,000 BTUs off of a medium pressure VAV coil. Now, you still have the sensible component to deal with in the building using your sensible cooling solution, whether it be chill beams, passive radiant cooling or heating, or variable refrigerant. But because of the reduced pump horsepower to move that sensible energy versus fan horsepower that would be otherwise required to move air throughout the building, there's a significant amount of savings to be achieved using a 100% outside air DX dough ash solution. And it adds another advantage for system efficiency as well. If you can handle your total building latent cooling using a DX dough ash on a chill beam system, that means your chiller won't need to supply 44 degree chill water. It can provide 55 degrees, 57 degree chill water. And immediately your central plant efficiency goes up considerably. So DX dough ash is an excellent solution. And here, psychrometrically, we can demonstrate why that is the case. So if we apply the hot gas reheat solution, we now post-heat the air after it's been cooled and dehumidified at the cooling coil without paying an energy penalty to do that, because we use the heat of rejection off of compressors to post-heat to serve heat energy to the supply air stream to a coil that's downstream of the cooling coil to provide free temperature rise at that supply air stream, being 52 degrees supply air to 60 degrees or 65 degrees or whatever might be necessary without having to worry about a reheat solution. So that is it for today's presentation. So just a quick review. We've covered a lot of information today. We looked at, again, and reviewed psychrometric terminology. We looked at medium pressure VAV systems and their psychrometric process. We looked at the challenge of providing 55-degree supply air off of coils to our more efficient buildings. We've looked at sensible and enthalpy heat recovery psychrometrically. We looked at a high-performance HVAC solution of displacement ventilation and what that means with side stream bypass air handlers that are designed to provide 65 degrees dry bulb, 58-degree wet bulb out of the air handler. And then we looked at custom DX DOAS solutions that can help us provide the necessary leaving air condition in order to maintain building design set point temperatures and humidity levels to take the best advantage of the energy efficiency these systems offer. Thank you very much for your time. Are there any questions?
We do have some questions in the chat. So the first one, we are located in the southwest near the Four Corners area, very dry. Our HVAC system has been the same since installed in 1999-ish. What are the ways that we can get a more efficient system?
The first question I'd ask, is that to modify the existing system, or are they looking at changing out the system they have?
Right.
But let's look at both of them quickly. If they want to use the existing situation, look at providing a 100% outside air or an energy recovery device that's manifolded to the outside air intakes of all the individual air handlers. That'll significantly reduce the outside air load on those DX units, if they're DX, I don't know. Even if they're not, even if they chill water. So that's one way to get some added efficiency out of an existing system. If they are looking at replacing the existing system, the first questions we would ask is, what is the building's use? What is the owner trying to attain? What type of efficiency levels are they going to look at? And then what is the available budget to support that? And depending on those conditions, we might look at a variable refrigerant solution. We might look at low pressure VAV systems, which are really one of the best kept secrets for a cost effective high performance system in the market today. We might look at chill beams, especially if they're historical buildings and they want to minimize the architectural impact on that redesign or whatever. So there'd be many different ways that we would go.
All right. Well, I lied. There was only one question. I answered the other question.
Okay.
So unless anybody has any more questions, I mean, feel free to come off mute if you would just want to ask it, type it in the chat. In the meantime, I will fill some dead air if anybody has any questions. I am working on getting the PDHs and last month's presentation onto the website, and then also today's. So I will have both of those done today. So look for emails from me for those. No questions came in. Oh, nope, no questions came in. Thanks, Brian. Another successful Dan presentation.
Oh, thank you.
And I was just real quick, I was looking through the opening poll questions that I asked that were just some standard demographic type questions. But one of the questions in there was, are there any topics that you guys would like to see in our 2025 schedule as we are starting to build that schedule for next year? There were a couple responses for the new refrigerant changes. And I just wanted to let you guys know that I am working on something that we will do soon. It won't be in 2025. It'll be quickly this year. So that is in the works. But Dan, I will share the rest of these topics with you. And just a fun demographic comment is that 51% of the attendees today have been in the industry over 15 years.
Interesting.
Yep.
Okay. Thank you for joining us.
And another question just came in. So Daryl, if you wanted to stay on while Dan answered this, if anybody else wants to stay on, if not, feel free to head out if you have to leave right at 1. But with a small classroom building having 10,000 square feet, would you anticipate a DOAS unit would be needed for a split system heat pump fan coils?
Yes, especially from what we've learned today, what we know today from the pandemic and the government's involvement in trying to achieve better indoor air quality, especially for our schools, not only to protect students, but our valued teachers. If you provide a decoupled 100% outside air, you're always guaranteed you're getting the outside air to the space necessary to maintain the ventilation rates. And the CDC and the EPA are arguing, increase your ventilation rates for healthier buildings. Well, we certainly want to look at that during flu and cold season coming upon us. And we've demonstrated that if adequately designed DOAS units with low dew point depression offer significant energy efficiency to a split heat pump design. And it should be given every consideration.
All right. Well, I will leave it there, Dan. If anybody has any more questions, feel free to reach out to myself or Dan or to your salesperson here at Veritech, and we can continue the conversation and look for next month's webinar registration opening up in the next week. All right. Thank you, everyone. Thank you, Dan.
Thank you very much. Thank you for joining us today.
We'll see you next month.
Thank you, Kelly.
Thanks.